Good day, everyone. This is Chris Bear back again for another round of discussions. I thought I'd just kind of regress a little bit and perhaps even do a little bit of a redux and go back to this concept of quantum numbers. If you remember from the discussion on quantum numbers, really what they are the results of calculations. Generally, when we talk about these calculations, we're talking about the Schrödinger equation. Really, three numbers fall out of the Schrödinger equation. And then another one, which is this concept of spin, inherent angular momentum of the electron, also comes out when we use later formulations of the Schrödinger equation that account for relativity. And we generally say we have a total of 4 quantum numbers. Well, what are quantum numbers? Well, quantum numbers really are a roadmap to the electrons, if you want to look at them that way. They tell us about the electrons in an atom. Again, because this is all probabilistic and kind of based on waves and probabilities, we don't really exactly know where an electron is at any given time, but we can kind of figure out, well, what general level of energy it takes, and then what, when we talk about orbitals, what sublevels of energy inside our primary level of energy these guys take. And then we can kind of calculate the probability or the probability distribution of certain orbitals, and that's actually where we get these funny little shapes. When you look at your your s orbitals are rather spherical or circular in shape, and then you have your p orbitals and your d orbitals and then your f orbitals, and they can all take on these really interesting shapes. And again, it's not a technical shape of exactly what the electron's doing. It's just a probability density. It's just the most probable area of finding an electron that's in that energy level and in that quantum state, based on the quantum numbers. So again, these orbitals don't tell you that an electron's moving in there specifically, or really what it tells us is that, well, if I were to look at the atom at any given point in time and I had an electron with these specific quantum numbers, there's a really high probability that I'll find it in this area. Okay, so let's just go ahead and review the quantum numbers real quick. I have the N number, and that's the primary energy level. And when we look at the periodic table of elements, that primary energy levels actually are period. So N equals 1, 2, 3, 4, 5, 6, and 7. Of course, we can have more theoretically, but all we know of, or all that we have as a practical matter, are these 7 energy levels. And of course, the periods are horizontal rows. All right. And then I have the next number, L. And that's your orbital. If you were to look at the periodic table of elements again, we talked about the quantum numbers. You know that there are different orbitals or different blocks. You have over here, in these two groups, you have your s orbitals. It also includes helium. Over here, here, and here I have different orbitals. So I have s here, p orbitals here, d orbitals here, and then f orbitals here. And what these are, if you want to look at them as sublevels of structure within the period. So I have my primary energy level, and then within that energy level I actually have these orbitals that exist. Okay, so we've got orbitals down. Then I have something called M sub L. What M sub L is that's our magnetic number. And really what it describes is the shape of an orbital. As you guys know, these orbitals can take on different types of shapes, and some can get very bizarre and very strange indeed. And that's primarily dictated by the magnetic number. And then the fourth quantum number is the M sub S, and that is the spin. We often describe spin as a particle like an electron in a magnetic field, and we say that it literally spins around on its own axis, kind of like the Earth spins around on its own axis, and that's what creates a day. Well, that's not really what happens with the electrons, but we often say that just because it kind of helps us conceptualize it. But spin really is an inherent measure, or inherent amount of angular momentum that these particles just inherently have, and there really isn't any classical way of explaining exactly what that would look like. Again, it's all mathematical. Okay, so we have our numbers, and again, they're kind of just a roadmap to electrons. They tell us where electrons are at, or what the highest probability of electron being is. So let's just go ahead and break these down. I know sometimes in chemistry they love to do these assignments, and they'll give you a primary energy level, and they say, well, how many different types of quantum numbers do I have? Well, let's just go ahead and do a few. So let's say that my n equals 1. So 1 energy level. And I want to know, well, what am I going to have for my L's, my M sub L's, and then my M sub S. Okay. Well, it's really easy for the primary energy level. If I have n equals 1, well, my L is always going to equal 0. My M sub L is always going to equal 0. And then M sub S, and this is really easy, is either plus 1/2, spin 1/2, or negative 1/2. And those are the only two numbers we have for the M sub S, or the spin. So if I look at this, I really only have two configurations for an electron in the first, if my n equals 1, that first energy level, or period 1. I have 1, 0, 0 plus 1/2, that's 1. 1, 0, 0, negative 1/2, that's 2. And if you remember from the quantum numbers discussion, what does the L, what does that mean if my L is 0? Well, that means I have an s orbital. And s orbitals only take on one shape, right? M sub L, I only have one thing there, and they generally take on a circular shape. And how many electrons can live in a single orbital? 2 electrons. 1, 2, and that's where I have my spin plus 1/2 and spin minus 1/2. So my primary energy level, n equals 1, I can only have an s orbital, excuse me, and I can only have 2 electrons. And do these quantum numbers, what I just did here, does it correlate to what we see? Well, let's go ahead and take a look at the periodic table. So I'm going to put this under here. N equals 1. Here's my primary energy level here. What do I have in period 1? Well, I have hydrogen, I have helium. Okay. Atomic number for hydrogen is 1. We know that in nature, that's the number of protons, and protons in a nature or neutral atom will always correspond to the number of electrons. So hydrogen has 1 electron. Does that fit with our quantum numbers? Yes, I can have 1 electron. It is allowed by looking at my quantum numbers. 1, 0, 0 plus 1/2. There's 1 electron. And we know that that electron, because this is in the s block here, lives in a s orbital, and we know that s orbitals are spherical or circular in shape. So everything, the Schrodinger equation, these quantum numbers so far are predicting what we actually see. Well, let's just do helium real quick just to make sure that everything looks good. Well, helium has an atomic number of 2, and we know that a neutral atom in nature has 2 protons, is going to have 2 electrons. Well, first energy level, L equals 0, and we do know that we just move helium over here because these are the stable noble gases, but we could move helium over here. We know that it is in the s block. So again, the M sub L, the orbital number, tells us that that second electron's in, or those 2 electrons are in an s orbital. And what do we know about an s orbital? Well, it can contain 2 electrons, and we have plus 1/2 and negative 1/2 for spin. So far, if my n equals 1, these quantum numbers do describe what I see, or what I see physically, is kind of coinciding with what I see mathematically. So far so good. Alright guys, I'm going to cut it off here, and then I'm going to actually post another video where we talk about some of the other quantum, or the other n levels. We'll do n equals 2, 3, 4, and so on. I think I'll just dedicate a separate video to those concepts, just so I don't kind of run out of time and space. Alright, thanks again guys, I hope that helps.